So because a lot of the stuff that we're going to be doing in this unit has to do with drawing, I'm going to try and do a couple of these document camera videos so you can actually see how to draw, not just read how to draw. So this page, this one page of notes is what you'll find on the assignment for lesson 3. And there was a little bit of confusion on this table here that was, there we go, that was on the last note packet, and I just goofed and didn't take it out. So we're going to talk about it now. So basically what we're going to do here is talk about basic structures of alkanes, alkenes, and alkynes and how to draw them. I mean, if you looked at table P and table Q, they're pretty straightforward, especially with Q. I mean, it tells you that the alkanes have this specific general formula, but then it even gives you a picture that shows you that all alkanes have single bonds. Same thing is true for the alkenes, showing you it has doubles, alkynes showing that it has triples. So, but we're just going to put that to use, and I'm going to show you how to draw it using specific formulas. So the first one we're going to do is going to be an alkane. I'm going to do one of each. Show you just basic, simple structures of drawing. So an alkane, such as, how about C5H12. Now, I know that C5H12 is an alkane, and I'm just going to kind of review from the last one because it fits the formula of CnH2n plus 2. This is given to you on table Q, and basically saying that N is whatever number of carbons there are. If there's 5, if I did 5 times 2, that's 10, plus 2, it's 12. Anything that fits this general formula from the molecular must be an alkane. All right, so skipping over the empirical for a second, or, well, let's just do it. C5H12 obviously doesn't simplify, so it stays C5H12. Now, the structural formula is pretty simple when it's basic organic compounds. The way I do it, and the way I think that we're going to do this throughout all of the drawings that we do, is we always just start with how many carbons there are. And in this particular one, there's 5. So what I do is I take a straight chain, like a straight line of 5 carbons. 1, 2, 3, 4, 5. And then I refer to the fact that it's considered an alkane. And all alkanes have single bonds. And so in between each of them, I do boop, 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 boop. Now, after you make a drawing like that, you have to add in the hydrogens. And to do so, it's really simple because every carbon can only make 4 bonds. And if each one of these has 1 or 2 bonds, we just add however many hydrogens equal out to be 4 total. So this carbon right here is making 1 bond. It needs 3 more bonds to a hydrogen, so it's going to take 3. I like to do them in 90-degree junctures because it just spaces it out perfectly so that you can work with the space that you have. This carbon right here is currently making 2 bonds, so we add another one, 2 more here, 2 more here, and 3 at the end because it only had 1. And that's how you would make a simple structure for an alkane, specifically the one with 5. Now, if we want to take this a step further, we could say that 5, according to table P, has a prefix of pent. I'm just going to put that here. It's an alkane, so I use the suffix here, and this would have a name of pentane. And that's it. So working with an alkene and an alkyne, I'll go a little bit more quickly because I think you get the gist of this simple task. I'm going to keep the carbons the same for both of them, but obviously the hydrogens are going to change because the number of the bonds in between are going to be different. Alkenes have a double bond. They fit a specific formula that would make this H10. Simplifying this out wouldn't. So it's just good practice for later in the year. And the same thing I did here, I'm going to do here, which is start with my 5 carbons all bonded together. I always start with single bonds, unlike the last time. This is really how I would start it, because then I would refer to here. Double bond. So for now, it doesn't matter where you put it. It's going to matter where you put the double bond, but for right now, we'll just put it on the first carbon, and then we'll add our hydrogens. So it's a step. It's a building process. You have to follow each one of these steps in order to do it correctly. So this carbon is making 2 bonds. Therefore, it's going to get 2 more. 1, 2. This is not drawn correctly, but I'm not going to bog you down with that right now. This carbon here has 1, 2, 3, so it only needs 1 extra. This carbon has 2, 3 bonds, 4 bonds, 3 bonds, 4 bonds, 2 bonds, 3 bonds, 4 bonds. And that's how you would draw an alkene. Same thing here, except the hydrogens change because it's got a triple bond. It would be H8. Again, it doesn't simplify because 5 is a prime number. And 5 carbons. 1, 2, 3, 4, 5. Triple bond can go anywhere. I'm going to put it in the same place just for now because it's fine. So I'll put an H here because it has 1, 2, 3. This makes a 4th bond. An interesting thing here with the triple bonds is this carbon right here, 1, 2, 3, 4. It already has 4 bonds. And so at this point, you don't add any more. It stays just like that. So then we just move on. 1, 2, 3, 4, 5, 3, 4, and then 2, 3, 4. And that's a basic, simple way to draw these. Now, the second part of this, we're going to get a little bit more complicated, and we're going to do that in a second. But I just wanted to go back here and just, add to the fact that C5H10 is also a pent prefix, but because it's an alkene, because it has a double bond, it's not pentane, it's pentene. C5 again, this is obviously pent, but now it's an alkyne, and because it's an alkyne and it has a triple bond, we just name it so that you could basically go from here, here, or here. This was your starting point, this was your starting point, or this was your starting point. You can figure out the other two based on counting from the picture, based on the number of carbons and what type of bonds are in it. And all 3 of these things are going to be interchanged in your tasks for figuring out what the other is. So an interesting thing comes up here. It's called an isomer. And this is the second part where we're going to take our drawings to a higher level. An isomer is, if you recall, we still do have a word of isotopes. And an isotope is something that has the same number of protons, but a different number of neutrons. There's a little review, right? Same number of protons, different number of neutrons. Forgetting this tope part, the iso comes from something is similar, but something's different. And so for an isomer, it has nothing to do with protons and neutrons. It has to do with drawings. And basically, it means it's got the same molecular formula. Okay, same molecular formula. C5H8 would be the same as another C5H8 or C5H10. But here's the different part. But it has a different structural formula. Different structure. Now, with all of that said, I just want to add to this. They're going to have this different... Damn it. What a ding-dong. They're going to have different chemical properties as well. And they're also going to have different physical properties. So, really, the only thing that's the same about 2 molecules would be their molecular formula. Everything else is going to be different. Their structure, their properties, both physical and chemical. And you're going to see in a minute its locations of bonds and things of that sort. So I'm going to ask you to do is try to draw two different structures of C4, yep, C4H10, also known as butane. 4 carbons, single bonds, 10 hydrogens. So when you try and draw two drawings that are different, and I'm going to stop the video and create a new one with the answers and the next steps, and I'll catch you on the flip side.